Let's work on this example. The force required to bend a 1 millimeter thick piece of steel varies with its temperature. Find the line of best fit that predicts the force given the temperature. So there, when we're writing this line of best fit, the variable that we're trying to predict, the y's, we're trying to predict the force. So our y's are going to be the force data, and the x's that we will use to predict the force are going to be the temperature data. Right? In correlation, it does not matter, but in regression, it does. So make sure you know what's x and what's y. All right, let's go through this. Find the line of best fit. Let's first plot these points. All right, so we have a temperature of 100, 120, 140, 160, and 180. 100 has a force of 1.29 newtons to bend the steel. 120 is, oops, that's actually my tallest value. So over here at 100 is 1.29. At 120, it's 1.25. At 140, 1.21. 160 is 1.17. And 180 is 1.04. So it seems like it's pretty significantly negatively correlated. Let's add this to the problem. Let's find the Pearson correlation coefficient. So my equation for R, n times sum xy's minus sum x's summed y's over n sum of x squareds squared x's, and same deal for y's. All right, and let's actually give ourselves these numbers. All right, n is the number of data pairs. I see 1, 2, 3, 4, 5. The sums of x, y's, I get 6, 8, 9, 2, 7. 0.2 minus the sums of x's, 700. Sum of y's, 527. 0.04. Here we have 5 times sum of x squareds, 102, 0, 0, 0, minus the sums of the x's, 700 squared, times 5, the sum of the y squareds, 7,000, nope, 70,000 and 79.8, minus the square of the y's, 527.04. All right, now when the algebra clears the room, we have a Pearson correlation coefficient value of minus 0.955. So that looks pretty significant. Let's double check. We've got 5 data points, meaning our degrees of freedom is 3. And if I look at the 5% threshold, it is significant. If I look at the 1% threshold, it is not significant. So 5% is pretty good. Let's say that it is significantly correlated. Right, that's a pretty strong negatively sloped line. Now let's actually answer the question. Find the line of best fit. Now, because you already have your R value, solving for your slope is going to be quite easy. Right, your slope equation is n times sum xy's minus summed x's summed y's over n summed x squareds minus squared sum x's. And you actually already have that because this numerator is the same thing as this numerator. And this denominator is this factor in the denominator. So you should already have that, make the algebra a little bit easier on yourself. the slope that we get is minus 314.5. Oh, actually, that doesn't make any sense. I made the same mistake that I urged you all not to. I switched my x's and my y's. If the x's are the temperatures and the y's are the forces, then my slope becomes minus 0.003. The y-intercept is then average of y's minus slope times average of x's. And we get a y-intercept of 1.60 about. So the line of best fit, y is equal to minus 0.003 x plus 1.6. So up here at 1.6 is where I cross my y-axis. And we have a slope of minus 0.003. Okay, so let's see. We found the line of best fit that predicts force given the temperature. Now use our model to make a prediction of the force required to bend steel at 400 degrees centigrade. So 400 degrees centigrade, let me get rid of some work here. Right, if we continue along our x-axis, our temperature axis, 400 is going to be somewhere over here. So the question is, what y value is this line going to give me at 400? So I just plug in the temperature, right? This is why it was important that the x's were the temperatures. I plug in the temperature of 400 into x, and then I see what y is. So y is going to be minus 0.003 times the x value of 400 degrees plus 1.6. In fact, I don't want to say y, I want to say y at 400, right? This is a function. All right, now when we do this, the y value that we get when it's 400 degrees, or the force that it takes to bend this rod at 400 degrees is 0.4 newtons. Okay, so it seems like as we heat up the rod, it becomes easier and easier to bend. Let's answer the last part. Let's now make a prediction for the force required at 1,300 degrees centigrade. So I need to clear off some even more space because 1,300 is way over here. In fact, it's probably too far away from our data to use our straight line to make a safe prediction, right? Our temperature data, we only collected data over the temperature range 100 to 200. So maybe even estimating at 400 was kind of a stretch. Estimating over here at 1,300 probably isn't a very good thing to do at all, right? The material is probably going to melt at that point, and this line is no longer going to be used as a good predictor. Let's see what we get, just in case. What is the y value at 1,300 degrees? I get a force of minus 2.3 newtons, which obviously doesn't make any sense, right? So our line cannot be used to make predictions if we ask it to make a prediction well outside of the range where we collected data.